Relational algorithm of the golden rectangle. Introduction. The following content describes the algorithmic procedure for generating a golden rectangle within the CLACL environment. The exposition is divided into sequential logical steps, illustrating the transition from ontological definition to graphic visualization, highlighting the distinct features of the generative geometry paradigm compared to traditional CAD systems. Step 1. Definition of triangular ontology. The code begins with the declaration of logical primitives. Through the command define model tris, the system receives the abstract definition of triangularity. This is not a drawn figure, but a closed topological graph composed of three instances cyclically connected by generic relations. This step establishes the internal consistency rules for any three-vertex structure generated thereafter. Step 2. Definition of quadrangular ontology. We proceed with the definition of the model square. Unlike the triangle, this model imposes specific semantic constraints. The relations are not generic, but qualified as base, height, and diagonal. This model acts as a structural validator. It defines the necessary conditions for four instances to be logically considered a rectangle or a square within the relational space. Step 3. Definition of graphic representation. The command shape_rect separates logic from visualization. While the previous models handle the mathematical structure, the shape instructs the rendering engine on how to translate graph nodes into visible perimeters. This level of abstraction allows for the manipulation of geometric logic without necessarily rendering it at every step. Step 4. Instantiation in the non-Cartesian void. The procedural execution opens with the commands !A and !B. At this stage, it is crucial to highlight the main theoretical divergence. The system makes no use of Cartesian coordinates. The instances possess no x or y values, nor do they reside on a pre-established grid. Space in generative geometry is not a graduated container preceding objects, but an absence of structure awaiting definition through relations. Step 5. Genesis of intrinsic metric. The instruction &RR connects the primitive instances. In the absence of an external or absolute measurement system, such as meters or pixels, this first relation founds the unit of measure for the entire generated universe. Distance is not measured against an external ruler, but is defined by the act of connection. It is a purely self-referential system. Every subsequent dimension will be relative to this first relational instance. Step 6. Fundamental triangulation. Via the instruction &R1, the system introduces a third instance bound to the first two. This operation of rigid triangulation establishes a stable reference plane. Without this step, the system would have infinite rotational degrees of freedom. The relation fixes the basic geometry upon which subsequent projections will operate. Step 7. Application of the triangular model. The command model tris is invoked on the current instances. This step applies the topological constraints defined in Step 1 to the current instances. The system verifies and consolidates the structural consistency of the nodes, preparing them for complex projection operations. Step 8. Relational vector projection. This is the crucial step for determining the golden section. The code uses the directional operator double greater than. The instruction takes an existing metric relation, the internal measure defined in Step 5, and projects it toward a new node. No coordinate calculation takes place. The operation is topological. A quantity of relation is transferred along a direction, simulating the turnover of a compass in a space devoid of Cartesian axes. Step 9. Derivation of the golden point. The subsequent instruction &R3 intersects the projected distance generated in the previous step with a new bound relation. The system calculates the position of the only instance that simultaneously satisfies the projected distance and the geometric constraint. The resulting point divides the reference segment exactly according to the irrational ratio of 1.6188. Step 10. Polygon closure. Having identified the four vertices through projections, the closure relations base, height, and diagonal are applied. These instructions do not move the points, but create the logical links necessary to define the quadrangular topology. It is the structural assembly phase of the final figure. Step 11. Validation via model. The command model square is applied to the four derived vertices. This is a verification phase. The system imposes the square rules defined in step 2. If the golden projection operations of the previous steps are correct, the vertices will accept the orthogonal constraints without errors. Otherwise, the model would reject the configuration, signaling a logical inconsistency. Step 12. Final rendering and numerical verification. The process concludes with shape span and the print command. The graphics engine fills the area defined by the validated relations, making the golden rectangle visible. Concurrently, the numerical output provides empirical proof of the algorithm's correctness. It is only in this final moment of output that the pure relational system is translated into readable values, confirming the golden ratio.